Hey everyone, welcome to the third video in our series on the reactions of Chapter 8. So in the last video, we talked about acid catalyzed hydration. So in this video, we're going to be talking about another form of hydration that does the same thing, sort of, that the last reaction did. There's just some advantages and some disadvantages to it as well, to this new form. So this new form is known as oxymercuration. Demercuration. And we're also going to talk about a variation on this as well, which is known as Alkoxymercuration-Demercuration. So kill two birds with one stone in this video. So this reaction is a Markovnikov reaction, okay? And it's a hydration reaction, right? So this is a hydration reaction. So it does hydration. So I add water across a double bond, right? Um, and another thing to mention about this is that it's Markovnikov, like I said. Additionally, we do form both the enantiomers. And the last thing to mention that I think is important here is that this reaction has no rearrangements. Rearrangements cannot happen and unless it's very rare circumstance. So rearrangements are not possible. Okay, so rearrangements are not possible in this reaction. That's why this is a good reaction to use sometimes, because we would prefer to not have rearrangements on some cases, right? There's some cases where we don't want to have a rearrangement happen. And so if that is the case, then we want to use a reaction like this to add water across the double bond and not have a rearrangement happen, right? Okay, so let's take a look at this here. So we'll start off with this alkene. And then my reagents for this are a bit of a mouthful. So my first step is HgOAc2, and then water with THF. So water with THF and HgOAc2 is the first step. Second step is NaBH4, which is sodium borohydride. So whenever I'm writing first and second step, that means that I add everything in the first step in, I wait for the reaction to happen, and then I separate all of that off, and then I add the stuff in for the second reaction. So this is like two separate reactions basically that are happening, and we need to know what the sequence of both of them combined gives us, okay? So like I said, this just gives us a Markovnikov alcohol. So we get this, right? That's what we get. All right. But there are some other things to know about this. Okay. So, as you can imagine, a hydrogen added here, right? We added a hydrogen to that carbon there, but we also add the OH in the Markovnikov position, right? And we can also form both enantiomers and all that stuff. But the thing that I want to worry about is that rearrangements cannot happen. So let's say, for example, I used this one. So move the double bond over here. And I put it through the same sequence or same scheme. So I'm using HgOAc, and OAc is just acetate. So it's a mercury with two acetates on it. And then my water THF. And then sodium borohydride. Okay, so now if I put this through, typically we would have a hydride shift and we would get this exact same product. But now, since this cannot undergo rearrangement at all, we get this and this. So we get the Markovnikov alcohol. So the hydrogen added here because there's more hydrogens, right? And the OH has to add to the other carbon. And the reason I drew this on a wedge and a dash and not this one is because this carbon is not chiral because there's two methyls on it, but this carbon and this carbon are both chiral. So I get both enantiomers when possible from this reaction. Okay, so both enantiomers do form. All right. So let's take a look at one more example and then we'll talk about the mechanism. So again, same thing. Okay, so same reagents, and then so I just add the alcohol to the more substituted carbon. And this isn't a chiral carbon, so I'm not drawing it on a wedge or a dash. That's it. So that's the entire reaction, right? So there's not, as long as you know the reagents, like there's not that much going on with this one. Okay. So don't be scared by the big list of reagents that we use for this. It's actually not too bad. All right. What isn't great is the mechanism. So let's talk about the mechanism. So I'm going to do the mechanism of this very first example that we had here. Okay, so let me erase these other ones that we just did. And then I will do the mechanism of this very first one. Okay. And this mechanism isn't important. I do not anticipate that you'll have to reproduce this mechanism on an exam, but at least for this course. But I think that it's important to know the intermediates for this. So I'll talk about the things that are important to know whenever we get to it. Okay. So the very first step is that I have HgOAC2. Okay. And so this HgOAC2 is able to dissociate in solution. So I have this HgOAC2 and it dissociates and loses one of the OACs. So then I just have HgOAC plus, and the plus is on the Hg, right? And then I have OAC minus. Okay, so I form HgOAC plus, and I also have OAC minus. So the HgOAC plus is what we're going to be using in this. And this Hg does have a lone pair. Okay. So now let's take a look with the mechanism. So now we have this double bond, right? And what's going to happen is that HgOAC plus with the lone pair, this is going to attack the double bond because it has a lone pair on it, right? So it's possible for it to attack the double bond. But at the same time, the double bond is going to attack back because this is positively charged, right? And these electrons are negatively charged. So it's going to attack and simultaneously attack back, okay? So then that's going to give us a very interesting intermediate that we do need to know, okay? So this intermediate is going to look something like this. So we have Hg, and this is bonded to the OHC, and the Hg is positively charged, okay? And then I have both of these groups, and I have this group as well. So now this is what I form, okay? So this is this has a specific name. This is a mercurium ion, okay? Mercurinium ion, sorry. So This is my mercurinium ion. And so mercurinium ion is an important thing to know. It's important to know that it goes through this intermediate. You may be asked what the intermediate looks like. So if we're trying to determine what the intermediate is, I just take the double bond and draw a triangle from each carbon that is in the double bond, and then put my HgOAc in there with a positive charge. And that's it. Okay. So that's how I form my mercurinium ion. All right. I need to erase the mercurinium ion so that way I can draw the next step. But that's that's what we're doing there. Okay. So now what we're going to have is water. We have water in the first step as well. So water is going to come in, and water is going to attack the more substituted carbon. So this carbon versus this carbon, which one is more substituted, left or right? Well, the left one is more substituted. I have 2 methyl groups versus 1 methyl group, right? So water is going to attack most substituted, which is going to break this bond, and the mercury is going to get the electrons from that bond. All right. So now what I have is, we're back to this, right? And then I have my water that I've added here, right? And then I also have my HgOAc that just got a lone pair as well. Okay, so I just add water, which is eventually going to become my alcohol, and then I have HgOAc as well. Okay, so now this step makes the HgOAc and the water anti to each other. That's not super important, but that is something of note. So those two things are going to be anti to each other at this point, but in the end product, it doesn't actually matter. So now the next thing that happens is that we take another water, and that water is going to come in and deprotonate what we just added. And then that gives us our alcohol, right? So now I have my alcohol, and I also have H3O plus that I just formed, right? Because that water just deprotonated. And then, but I still have this issue of this HgOAc on there. So now I need to find a way to get this HgOAc off. Okay, so how do I get this off? Well, what I need to do is add NaBH4. Okay, so that's my second step, NaBH4. So I'm going to draw this arrow down, okay, and I'm going to put NaBH4, okay, and then what that NaBH4 is going to do is this. So we still have my HgOAc. And NaBH4 looks like this. So it's a boron with 4 hydrogens. This is minus, has a minus charge, the boron. Then I have my sodium here. So sodium and boron with the 4 hydrogens sitting there. And one of these hydrogens is going to attack this carbon that has the mercury on it, and the mercury acetate leaves. And then I'm done. So what just happened in this last step is that this HgOAc just got replaced with a hydrogen, okay? It did an SN2 reaction basically, and it got rid of the hydrogen, or it got rid of the HgOAc. The hydrogen got rid of the HgOAc, okay? So that's all that's happening there, okay? And then I also get some byproducts as well. I would not worry too much about these byproducts, but I just want to be concise in this and say that BH4 just lost a hydrogen. So now it's BH3. So I also get BH3. And then I also get sodium with a HgOAc minus that has 2 lone pairs on it. So I get sodium HgOAc. Okay. So I get BH3 and the sodium HgOAc as well as my product. But these these things here that I've listed, I'm doing this to be concise. These are not important. But I'm just letting you know that is what you get. Okay, so I wouldn't worry about that too much. But um, yeah, I just want to be as concise as possible in the mechanism. So, but everything else here, this is a decently challenging mechanism for where we are in the course right now. And the most I think the most important thing to know here is this triangle 3-member ring intermediate. Okay, you may be asked to draw this, and like I said, just take where the double bond is and then draw the triangle there with the HGOAC and put a plus. That's the intermediate. Okay, so that's the intermediate. So since I don't have a carbocation intermediate, that's why I can't have rearrangements in this reaction. Okay, rearrangements just can't happen. It's just not possible because of that. Okay. So now I want to talk about a variation of Oxymerc, which is known as Alkoxymercuration-Demercuration. So now we have Alkoxymercuration-Demercuration. So before we had Oxymerc, right? So oxy is referring to oxygen and water. So I'm adding water. In Alkoxymerc, I'm not adding water, I'm adding an alcohol. So alkoxy, alkoxide, right? So the alcohol, I'm adding an alcohol. Other than that, this is exactly the same, right? It's Markovnikov. I also get both enantiomers and no rearrangements. So I'm just going to do 2 examples of this. The mechanism is exactly the same. I'll explain the difference. And other than that, we're just going to do 2 examples and that's it. So I'm going to do this one, and then I'm also going to do this one. So we've already seen these 2 molecules, right? So the only difference is that I still use my HGOAC2, but instead of water THF, I have an alcohol. So in this case, I'm going to use methanol, but you can use any alcohol. So propanol, butanol, isobutanol, isopropanol, anything. And then second step is NABH4. So you'll notice everything's the same. Water just changed to an alcohol. That's it. So now my product is also going to be exactly the same, except instead of adding an OH, I just add O and then whatever the rest of my alcohol is. So in this case, it's OCH3. So I add OCH3. So I'm making an ether, right? Making a Markovnikov ether. So that's the only difference in this, okay? It's just important to point this out because this is easy to overlook, whether it's a water or an alcohol. So that's why it's important to pay attention to this and know whether or not you're doing Oxymerc or Alkoxymerc. Okay, so again, HGOAC2. And in this time, I'm going to use ethanol. So CH3, CH2OH with THF. And then I'm going to have NABH4. Okay. So now, again, we can't have rearrangements. So I'm just going to get this and the enantiomer. Just like the one where we added the OH, except now it's just O and then the rest of my alcohol. So in this case, I'm using ethanol, so it's OCH2CH3. So I add ethoxide. So either way, this is making a Markovnikov ether. Okay. So we have Oxymerc versus Alkoxymerc. So pay attention to what we're using, whether it's water or an alcohol. And then just know that this is Markovnikov. We form both enantiomers and we have no rearrangements. So like I said, mechanism is not vital, I don't think, but I think that it is important to know that that mercurinium ion intermediate. Okay. So in the next video, we're going to be talking about the last form of hydration of alkenes, which is hydroboration oxidation. So hopefully you'll join me for that. I appreciate you watching this one. Hopefully it was helpful, and I will see you in the next one.